Hello and welcome. Now that I've found my way around NitrOS-9, it's time to start getting technical. So today we're going to have our first of a series of more technical deep dives into NitrOS-9. And today we're going to write a Hello World app in assembly language as runnable by NitrOS-9. We are going to go into the LWASM command line that I used and the various Toolshed commands that I used to transfer things between my host and the virtual hard drive. We'll talk about how to make OS9 API calls. We'll talk about what the module header is all about and how you set it up, the difference between data addresses and code addresses, and how they're crucial to NitrOS-9 module memory management. We'll talk about PC relative addressing and in general what position-independent code is and why you need it. And we'll step through it all in the MAME debugger to see what the code does. I didn't realize that all of those considerations were going to be necessary, and my first version of the Hello World app did not take all of them into consideration. It looked fine, it looked reasonable, but it was riddled with bugs. And one by one, with help from the folks on the CoCo Discord, I found those bugs and I fixed those bugs, and I found it a useful way to learn about NitrOS-9. So that's how I'm going to be presenting things to you. I'm going to show you the original version of the Hello World app. I'm going to talk about it as if it were totally fine and there are no bugs, and then one by one I'm going to introduce those bugs and show them to you. It's a pedagogical technique known as lying. So I warn you not to take that first version of the code and say, all right, I've seen enough, let's just run with it. And you're going to kind of need to watch through the end to see what the final version of the code is. Or if you're impatient, just check the description. There is a link where you can go and find the final version of the code, and you can just start with that and then ignore this whole video. That's fine. I don't really care. Anyway, I'm excited to get going, so let's get going. Here's our Hello World program. We start off doing some include business and whatever on earth that is. And we got some name business here. This is pretty recognizable. This is the message we're going to print. We're going to print Hello World. And then if we come down, this is the actual body of the method that actually does things. And there's no loop. We've got a string of characters and we don't actually loop through it character by character, but we do have some weird $ things here. And OS9, that's at a 6809 instruction. And then emod, oh goodness. Okay, it's true there is some stuff, some overhead we need to learn about. But beyond that, there actually is not much going on here. This is actually, in a sense, easier than if we were to do a Hello World program on just the regular CoCo with the disk extended basic ROM, and that was it. OS9 has all sorts of system calls that make a lot of things easier for us, including printing a message. Let's start here. OS9.d is a bunch of definitions that our code can use to help us call things and to help us set up constants. These are the names of a bunch of functions that we can call, some more functions we can call, some more functions we can call, some constants that are useful, some signal codes, status codes, all sorts of goodies. Where did I get this file? When you install EOU, you get a whole bunch of files. And if you go into the hard drive that they give you, you'll see that there's a defs folder. And here's a whole bunch of defs that you might be using in your code. It turns out the only defs that we're going to be using is that OS9.d file. I didn't know that at first, so I just copied all of this to my hard drive so I could take a look at it. You can use Toolshed to inspect the hard drives right from the comfort of your very own command prompt and the operating system of your choice. And until now, I've been using the decb executable from Toolshed. That's what you use when you're playing with disk extended color basic disks. OS9 is the executable you use when you're doing OS9 disk stuff. And the rest of it is quite similar, so I can do OS9dir. And that's the name of the VHD for the hard drive that contains everything. 1 comma later, and it'll print out everything there. If I go into the defs folder, then I get to see all the nifty files they have. And with one command, I can save that entire directory onto my hard drive on my PC. So we'll go into my sys folder, which is currently empty, and I'll do the dsave command. And two options I'm going to add are -e, which says actually execute the dsave command rather than telling me what you would normally do, and then -l to fix all the line feeds for my operating system. And then at the end, the directory I want it to copy everything to. So now I've got everything here, and I can take a look at them, which I did. And I decided that this os9.d file is really the only thing I need, and I don't need very much from here to begin with. So congratulations, we've gotten through line 2. We haven't even gotten to line 1 yet, though. So this file needs to know some stuff about how you're going to be using it, and one of the things is it expects you've defined this constant to tell it whether or not you're using the 6309. I'm not, so I set an equate for that to 0 at the beginning, and then including this will happen fine. Otherwise, LWASM has an issue with this thing not being defined. The next part is probably the most overhead you're going to have to deal with cognitively when you're doing OS9 stuff as opposed to other stuff. You've got to give LWASM enough hints so it figures out how to write the header for the module that it's going to generate. Everything that you run on OS9 is a module, and it looks like this, where you have the header, you have the stuff, and then you have a CRC checksum at the end. Breaking it down even further, the header needs to consist of these different attributes. And breaking it down even further, these tell you what the offsets in the header are that relate to these different attributes you've got to put there, and then it defines all of them. And I'm getting all of this from the NitrOS-9 EOU Technical Reference Manual, which is one of the docs that you can download from L. Curtis Boyle's website. I have links to everything in the description. So a bit later, we're going to take a look at exactly how this got baked into the binary, and we'll actually look at the header. But for now, we got to understand what these things are that LWASM needs. They relate to the header, but they're not exactly a one-to-one relationship. The first parameter needs to be the full length of the module. So being a lazy person, I don't want to calculate anything, so I just create a label at the bottom for length, and it will just put the value of that label here. One thing to note is that when you're compiling a module for OS9, there is no start address. There is no execution address. Everything just starts at 0. Every module you build starts at 0, and then OS9 decides where it's going to be loaded. So if I'm starting at 0, length will simply tell me what the very final offset is, and therefore the length of the module. Next up, every module has a name, and we need to put the offset from the beginning to where the name is. Since I'm writing a Hello World app, I'm going to use the string Hello World. Next up is the type of the module. These are constants that I picked up from that os9.d file. The first piece that I add together is one of the module type values, and we're writing a program, so I'm using the program label for that part. And then I need to add to it one of these that says what the language is. Since it's just a regular good old-fashioned 6809 object code module, I'm using object for that second part. Program plus object. The next is the set of attributes for this module added together. These are the attributes flags, and I'm just using this for a re-entrant module. But in addition to this, we're also supposed to include a version number. So while the upper bits contain these flags, the lower bits contains the version number. So I'm just adding a 1 because this is version 1. Next up, an offset to where the code begins. And again, I'm a lazy person, so I'm just going to put a label where my code begins, which is here. And I'm going to use that up here. And finally, it needs to know where does the data section end. It's actually the exact same address, but just for completeness, I'm using a special label here. So the two pieces of data I have are the name that I already talked about, and then this, the message that we're going to print. And that should be enough to give LWASM everything it needs to fill out all the bits for the module header. And that brings us finally to the actual body of the code. In order to print the message, I'm going to call a function call, an OS9 system function call called write. IWWrite is indeed one of those constants that's defined in os9.d, but most importantly, it's in that document, which gives us all of the technical reference information we need to write programs. And it helpfully tells us all the registers to set up before we enter the function, and then what to expect the registers to be in when it comes out. It seems that it's a common practice that these functions will set the carry bit in the condition codes if there's an error. That way you can use a branch on carry set or a branch on carry clear if you want to handle the error. And if there were an error, the B register would contain the error code. Otherwise, if all goes well, the Y register will tell us how many bytes were written. One thing that they're not telling us is there are special values for A if we want to write to standard out, or if we're doing a read operation, how to read from standard in. When writing to standard out, you use the special value of 1 for A. X needs to be the starting address of the data. So I load X with the address of message start, which is defined up here. Y needs to be the number of bytes we'll write. So I just do some simple arithmetic and subtract the end minus the start. And finally, I call the method by using this weird pseudo opcode OS9. The LWASM docs tells us that OS9 is simply how you make a system call. Behind the scenes, what LWASM is doing is when it sees this, it converts it into a sweet2, followed by a byte representing the function that you want to call. So this generates a user interrupt with the place you want to go to immediately after that interrupt instruction. Rather than forcing us to write that gross, disgusting stuff, we only need to do the OS9 stuff. Once that's been written, it's time to return, and of course you don't just RTS like you would in DEC-B. Instead, you need to exit, so you need to call the exit routine. This time it's us who's returning an error code, so we're clearing B so that the carry condition code is cleared, and then we're calling the exit routine. And the exit routine is just a function like anything else. And again, the docs tell us what the entry conditions are. And the exit condition is your process is terminated. Finally, emod tells us we're done with the module, end module. This thing up at the very top began the module, and this here at the very beginning ends it. And that's all there is to it, except for the fact that I have carefully hidden from you a few bugs. First time I wrote this was really the first time I was writing any kind of OS9 assembly language code, and I was doing the best I could, following the documentation and looking through some old docs as well. But there were still some things that eluded me. More on that later. So it's time to build this and to add it to our hard drive. The commands I'm going to show you I keep in a batch file so I can just run them all at once for convenience. But I'm going to go over them one by one. The first is the LWASM command. Much of it is what I normally do. I normally do -9 to limit myself to the 6809. I do a -O to say what my output file will be. My output is just going to be HW. Then my input file, which is hw.asm. And I'm going to generate a list file named hw.list. What's different is I'm saying that my format is now going to be OS9. By default, the format is DEC-B, so I need to tell it it's going to be something different this time. And so now I have my HW and my hw.list. And if we take a look at the hw.list, you'll see it does indeed start at 0. Now up here is all the stuff that I included, but my code starts around here. And you'll see my stuff starts here at 0 and then goes up until the end. My next command is to copy that file onto my hard drive. So just like with DEC-B, I'm doing an OS9 copy. -R means rewrite if it's already there. The source is HW, that's right here on my PC hard drive. The path to the VHD, comma, and then what I'm going to call it there. So I'm just going to put it in the root level of the user VHD. Now you'd think that would be all, but it is not. One of the things we can do is we can ask what are the attributes of any file on an OS9 VHD? And you have to spell that command correctly or else it won't work. And here we can see we can write to that file and we can read that file, but we cannot execute it. So each and every time I run the adder command with -E to add the execute bit. And now we've got the E and I'm allowed to execute. And now we're ready to enter NitrOS-9. I'm going to switch over to my Shell Plus window. I'm starting off on the drive that comes with EOU that contains the full EOU distribution, but that doesn't have my stuff. So I'm going to move over to my stuff, which is called the H1 drive. And if I do an ls here, I will see my HW, and it's got all those attributes that I want it to have. And here's where the problems begin. Let's run it. No! Maybe I need to do this. No! What's going on is that in OS9 there are two current paths. The one that I've been modifying is the data directory. The command to change that is chd, or cd is an abbreviation of that. This only determines the default data directory. It has nothing to do with where it's going to find the commands to execute. For that, I need to change the default execution directory, for which I use chx. You can use pxd and it will tell you what the current execution directory is. And as you can see, even though my current data directory is /dd, the current execution directory is /dd/commands. And I could even cd into there, and I could ask, well, what's in that directory? It's all the commands! Here's something fun to try. Do an ls instead of a dir in that directory. Too much for ls. I should try ls #k. What? Now here's something I do not recommend you do. You could just change the current execution directory to be the root of your user hard drive. Now, if I try to run hello world, aha, it works. But a bunch of other stuff has stopped working. For example, can I do an ls? Nope. Can I print the current execution working directory? Nope. The irony is that by changing the current execution directory, I can no longer print the current execution directory. I need to change it back so that my regular commands start working again. The alternative that I prefer is to simply change the path. If I do path equals h1, now I can do my hello world app, and that works. And I have my ls and everything else available to me. I'll bet there's even a way to configure one of the startup files so that the path is set for me every time I start up OS9. I should look into that. Did you notice that my Hello World app actually doesn't work? I asked OS9 to print Hello World with heightened emotion, an exclamation point at the end. It's printing Hello World with a period. It's as if it is tempering my emotions because it thinks that an exclamation mark is just inappropriate. That's not really what's happening. What's happening is that this is the first of many errors that I made that I will be going over. If we go up here, this was the name of the module, and I'm using FCS because that's what you're supposed to do for the module name. The S says that it will take the final ASCII character and set the high bit. That's the indicator to OS9 that that's the end of the string. When it came time to put the string I want to print into the code, I used FCS as well because I was not thinking. You only want to use FCS when you really want that high bit to be set. Alternatively, you can use FCN and it will add a null at the end. But what I really want is just an FCC. Don't touch the string, don't change the string, just make the string what I tell you to make it. This needs to be an FCC. There's that exclamation point. But that's not all. I've been told that having the name of the module be different from the name of the command or the name of the file is not advisable. I should actually have the name be this. I think I've been getting kind of lucky that it worked at all. The next problem is that I've been including the message that I'm printing as part of the data. As you can see, the code start and the data end are both right here. That leaves everything above here to be part of the data. Thanks again to the friendly folks on the CoCo Discord, I've learned what data really means. Data doesn't mean the stuff that's not code. Data means stuff that you change. Any memory you want to write to is considered data. Constant strings you're not going to write to, and they are not considered data. Why does this matter? Marking a series of addresses in the assembly file as data using this mod statement up here changes values in the module header, and that tells OS9 how much memory to allocate for the data section of the app. And the idea is this. I'm creating a re-entrant module, a module that could be shared by multiple processes, multiple users, and anything that's read-only, including the code and these strings, do not need to be loaded into memory multiple times, regardless of how many processes are run with this module being executed. The data area would be for things like variables. So let's say I wanted to reserve 4 bytes for some stuff, and I'm going to be writing to that stuff. What I want is for each process to have its own allocated data area with this amount of memory allocated for stuff. And every time the body of my function wants to modify those bytes, it will be modifying the bytes that were allocated to that process. Any other processes running this module will not get to see those bytes. This way I could have 100 users running. I don't need to waste memory by having multiple copies of the code. Instead, I just ensure that each process has its own dedicated data area with its own version of the stuff bytes. Now that I understood what data really is, I was finally able to make sense of this. In the LWASM manual, as it talks about OS9 modules, it says that it implements the standard data code address stream. That means between mod and emod, any RMB, RMD, RMQ, or equivalent directives will move the data address ahead and leave the code address unmodified. If you take a look at the listing file, you can see what they're talking about. This is a listing file from my Moon Patrol game, which is not OS9, it's just standard Deck B. And as we scroll down and start looking at the code, you'll see on the left it tells you where the address is that instruction is going to be assembled to. You can have code that continues with these addresses, and in the middle you can have an RMB, which just continues to move that address pointer forward. But in OS9 there are 2 address pointers. There's the one for the data, and there's the one for the code. So just by way of example, let's add a few more pieces of data. When we start at the module statement, our address pointer starts at 0. This is the code address pointer. But right after that, I start declaring some data. And LWASM knows it's data because I'm using RMB. In fact, anything that emits bytes is not data. Anything that doesn't emit bytes is data. RMB does not emit anything. All it does is it reserves some space. Something like FCS does emit stuff, so that's considered code, which is very convenient because I was supposed to be considering this code in OS9 as well. By the way, if I made one of these a ZMB, which initializes that area to 0, suddenly this is emitting bytes, and now this is considered code and not data. But for now, we're considering it data with the RMBs. So the address of the very first RMB is 0, and the dot at the end means we're talking about a data address. After 4 bytes of that, our stuff 2 is declared here at address 4, and 2 bytes later, stuff 3 is declared here at address 6. Next up, we're doing what is considered code. So we're back to the code address, which is at 000D. The reason it's at 000D is because that's how many bytes that module header took up. So this D is continuing this 0 address that had all those bytes for the module header added. And from this point forward, we're only moving forward the code address. If I wanted to intermingle yet more RMBs here, of course it wouldn't run and it would be terrible, but we could see even more clearly how the different address pointers get advanced. So the code address has advanced to 1C, where we're ready to start our actual code. And then right after that actual code, I had some data, and that data has the dot. And so now we're continuing the data address, which left off at 6 with an RMB of 2. So 6 plus that 2 brought us up to 8. Now we're back to code, no dot at the end of that address. Now we're back to data, we have a dot at the end of that address, code, data, code. Now, of course, this is crazy nonsense. So it's time to start organizing things properly. First up, I'm going to move my message after the data, right here. Let's get rid of this nonsense. So now the expectation is that this label should be 0 because we have no data anymore. This is all code. This is the name of our module. That's all code. This is the module header. That's all code. And then, of course, everything after that is all code. But I'm wrong. It is true that we're not advancing the data pointer at all. But let's take a look at what the data end label evaluates to. F. And if we take a look at the module header, data end is going to be the last part. And sure enough, that's our F. There's really different kinds of labels. I didn't have to worry about this when I was doing my DECB programming, but it definitely matters here. If I simply do this, if I equate data end to be dot, a dot sitting alone like this evaluates to the current data pointer. And if I go to the end, this length is properly going to be the current value of the code address pointer. But just to prove a point, I'm going to equate this with asterisk, which also evaluates the current code address pointer. So the rules as I think they are asterisk is current address, dot is current data, a label that's just on its own line with a colon is current address, and a label on the same line as an equate is going to be whatever that thing is. So in this case, it really will be the current data address. Let's try it out. Now my data end is properly 0, and you can see the last word of the module header is now 0. If I go down to the length, that is still properly the length of the whole module. And you can see that shows up here. But there's still a problem with this. Another thing I wasn't aware of is you've got to set up your own stack space. The Tandy OS9 Level 2 Development System document has a pretty handy diagram that shows how the registers are going to be set up when your code starts executing. Note, by the way, that the low addresses are at the bottom and the high addresses are at the top. So it's going to set your direct page and your U register to be the lowest address. Since this is all the data area, it all starts at 0. So U and DP are going to be 0 when your code starts executing. Y is going to point to the highest address allowed for you to write to in your data area. But check this out. Your stack pointer is also in the data area. It and X are going to be just under this parameter area. This is whatever the user might be passing on the command line when they call your module. In my case, they're not passing anything, but I still see the line feed character. So there's still a 1 byte difference between Y and these. But the important part is that my stack pointer is going to be pointing here almost near the end of my data area. And as I push, it's going to push it to lower and lower and lower and lower addresses. So my data area is not only for my variables, it's also for my stack space. So I really don't want a 0 byte data area. That's not a good idea. So I'm going to do this. I'm going to reserve 100 hex bytes just for the stack. And remember, this has to be the thing that I put at the bottom. So if I wanted any other variables, they would all have to go above. And that's because the stack pointer is always pointing at the highest address in the data area just after the parameters. Of course, I don't want this, so I'm not going to do that. So when I assemble this now, you'll see that my stack starts at 0 and then goes up to hex 100, which is the new value of data end. And you can see that hex 100 right here at the end of my module header. This is still not right. There's still more I need to do, but I'm going to run this anyway. So this time I'm going to run it by just typing in the full path rather than doing that path variable stuff. And it works. But the thing is, it shouldn't work. It's only working because of a bug. My favorite kind of bug, the bug that makes your code work. If we step through the code, you'll see we've been loaded into the page starting at EOU. Because right now on this line we're at 1C. And according to the listing file, the offset 1C is indeed where the code begins. So we'll load A with 1, and A is now 1. Now we're going to load A with where the message starts. Remember, the message start is now part of the code. It's not data. So it should be loading it with EOOF. But X is just loaded with F. There's no E at the beginning. We're no longer in the code section. We're actually up in the data section. I went through all that effort and that long explanation to explain that this is now code. This is the code address. I'm loading with the code address. What's going on? Why are you giving me the data address? And even more interestingly, why is it still working? If I take a look at my data area, remember that's starting at 0. And X is now loaded with F instead of EOF. And if I take a look at F, it starts right here. Hello world. The data area just coincidentally happens to have exactly the bytes I need it to have to make this work, even though I'm doing it wrong somehow, somewhere. When I investigated a bit further, I saw that this data area happens to come pre-equipped with all the bytes of the module, starting with that sync code, the whole header, the FCCs, even the bytes of all the code, and down to the CRC at the bottom. It's the exact same bytes as if I were to look at the module in a hex editor. Exact same bytes. My only guess is this is just an accident. The physical RAM that was assigned to our data area probably happened to be used previously to load the module in the first place. So I just so happened to be given that same physical RAM from my data area, which made my bug, whatever it is, invisible. Of course, I can't rely on this happening all the time if you have a whole bunch of modules going on. Or if I chose to write to my data area, all heck would break loose. In fact, let's do that. Let's add some code right here to initialize our stack area with 4242. We're going to write this word starting at 0, the very beginning of the data area, advancing X each time until we exceed the end of the stack portion. So we're going to write all of those bytes all around here. And once we do that, the hello world message that was accidentally there will get overwritten with a bunch of 42s. So let's step through that code now. At the very beginning, my data area still has the hello world there that it probably shouldn't have. And now I'm going to start writing 42 all over the place, which I am legally allowed to do. This is my area. I could do whatever I want. And you can see my hello world is already getting filled up. Now that we're all filled with the 42s, let's continue and see what it prints. As expected, the B's. So now my bug is properly causing things to fail rather than some other artifact of OS 9 hiding it and making it look like everything was fine. Have you figured out what my bug is yet? The bug is in this line right here. I am forced to write position-independent code. I don't know where my code is going to load. Right now, the logical address starts on the E0000 page, but that could change if I add more code, if I make it bigger. It could start loading a little earlier in memory. I have no control over that. That means anytime I need to branch, I had better be using one of those relative branches and not a jump. It also means that when I want to refer to a string that's in my code area, I can't just load it with this label. This label is just that code address that LWASM was maintaining starting at 0. Loading X with message start is always going to load it with F, no matter where I am. I need to turn this load X into something that is position independent, something that is based off of the program counter register. So this line must become this line. This tells the CPU to load the effective address into X, which is whatever offset message start is from the program counter. Message start is still F, but now this is going to calculate the offset from where the PC is going to be right after that instruction to F. Since we need to go to an earlier address, this is going to be a negative number. It's going to calculate F minus 2E. F minus 2E. E1. Check it out, folks. E1. This should prevent X from pointing into the data area. It's just going to go up to where the string resides in the code area. Now let's run the new code. We're now at the top, and hello world is still in our data area. Let's skip past all the writing. Now we got a bunch of 42s. And now when we load our X, it's EOOF, not OOOF. And if I take a look at the code area, you'll see right at EOOF is where my hello world string really is. Let's see if it worked. Hello world. I hope you found that interesting and informative. I definitely had a good time learning about how all this stuff works. I found it really cool. Coming up next time, we're going to dive into the CoCo 3 MMU, Memory Management Unit. We're going to learn how to program it, what it's capable of doing, as it is a critical part of how OS 9 Level 2 manages memory. Until then, have a great day.